brief introduction about today's resource person, Dr. Gurminder Singh. It is my pleasure to introduce Dr. Gurminder Singh, who is currently working as assistant professor in the Department of Mechanical Engineering at Indian Institute of Technology, Bombay, India. Dr. Singh has an impressive academic and research background, having worked as a postdoctoral researcher at the University College of Dublin, Ireland, and previously as a postdoctoral fellow at CIMAP Lab, University of Grenoble, Alpes, France. His research at Grenoble focused on experimental and simulation studies of extrusion-based 3D printing of metals. Dr. Singh was awarded the Gandhian Young Technological Innovation Award in 2020 for his groundbreaking work in developing a 3D printing method for fabricating patent-specific stents. He completed his PhD at IIT Delhi, where he pioneered a low-cost rapid manufacturing technique using ultrasonic vibration assisted sintering and 3D printing. His PhD work gained international recognition and was featured in the 3D print website Feb 2020 edition with 55 plus publications in leading peer-reviewed journals, conferences, and book chapters. Dr. Singh was contributed significantly to the field of additive manufacturing, material science, and manufacturing processes. His research has been published in prestigious journals such as Additive Manufacturing, Material Science and Engineering, a Journal of Manufacturing Processes and Rapid Prototyping. We are honored to have Dr. Gurminder Singh in ATAL FDP. We look forward to an engaging and informative session with him. Thank you, sir.
Thanks for the introduction. I would like to thank Aditya University for inviting me to give a talk in this FDP in AI and simulation additive manufacturing. So I will try to talk about innovative design and analysis in additive manufacturing, and we'll try to talk about some innovative new type of indirect metal 3D printing process. Let me share my screen. So I will talk about a new type of innovative type method of indirect metal additive manufacturing. There are now these days metal 3D printing processes like laser-based processes. Laser-based processes, electron beam processes. Okay, so but I will introduce a new type of indirect metal additive manufacturing which has gained significant popularity in last 5-6 years, which is because it is very cost effective, and it is very innovative to use it for different type of materials which are very difficult to print by laser-based systems. I will talk about a copper material, okay, which we try to develop a new type of process, which is indirect metal additive manufacturing, and it is having cost effective, and it can
Sir, your audio is not clear, sir. There is no audio, sir.
Sir, kindly switch on your mic, sir. Dr. Singh, sir.
Dr. Zubair, can you see my screen?
No, sir, it's not
Hello.
visible, sir.
Hello.
Previously it was visible, sir. Now it's not visible.
Hello. Dr. Zubair, can you hear me?
Yes, sir, your voice is audible.
Okay, okay. I apologize. There was some network problem. Okay, let me share my screen again. Can you hear me, please?
Yes, sir, your audio is clear
Okay.
and your
And videos also.
yes, clear. The
Okay,
screen is clear.
thank you. Yeah. So everyone knows about additive manufacturing. This is a process of joining materials to make object from three-dimensional model data using a layer-by-layer method. Okay. So initially it started with the rapid prototyping because people are using this process to make prototypes and using any 3D printing technique as just a prototype to start the initial design of any product. But now these days people are directly using it to make direct products. That's why we are calling it as rapid manufacturing also. So there are some examples I've kept, like these are the jaw implant, which is directly used as a product made by 3D printing. 3D printing process is started from a having a CAD model. It can be of any type of software, Creo, SolidWorks, or it can be of any type of coding. Even having a curves, you can make a surfaces which can be converted into tessellation files. Everyone knows about tessellation. It's approximation of the triangles of the CAD model, which is giving you the triangle values of the vertices and a normal, which can be used to generate support structure and slicing methodology, where you are slicing it in a single in a plane with having an offset and finding out the uh, points, connecting points, and making a G code for any type of 3D printing process. It can be FDM, it can be SLS, it can be your SLM, any type of process, but the steps are generally same. Only difference in the machine and the software of the machine. And later on, there is a step for post processing or finishing of the parts. So STL file is really important in 3D printing because it is the approximation. It is not a complete information of the CAD file. If you can see, this is a STL file and this is your CAD file. There is some missing information is left. So it will not give you the accurate uh, design features in the 3D printing part. Even in the inner part, like you can see inner part, this is STL file and this is actual file. You are having extra part. Okay, so you need always need some finishing to get to match with the dimensions. But now these days there are some another the new version of STL file which is called as AMF also. So it's called as additive manufacturing format, in which instead of having triangles, your in the triangle edges, you can have a curved type of edges, which will give you better approximation. So this is a complete new topic in 3D printing, where people is working on dimensional accuracy with having this format as compared to the STL file. It is now this available in the new versions of every most of the softwares. So it could have another lecture. So I'm not going in detail of this, but it is very interesting to see if someone is interested in file formats, they can explore this EMF file for having better accurate parts as compared to the previous version of STL file. You have seen metal 3D printing like SLM, where you are having a red laser. It can be different type of it can be it can be CO2 laser, it can other type of laser, fiber lasers, which is falling on a bed of a powder, which the bed is made by using a roller, which has rolled the powder from one bed to the another bed, which is a printing bed, and your laser is falling on it, and it is melting the powder and joining it with the previous layer and making a 3D printing part. But this process is valid only to those materials which can be easily observed, which are having good absorption coefficient, which can easily observe light photons, which should like steel, which is having less thermal conductivity. It can easily absorb titanium, which is having low thermal conductivity. It can easily absorb the energy and can melt the powder easily. But this type of process is very difficult to fabricate parts like copper, which is having very high thermal conductivity, and silver, aluminium, pure aluminium, not there are some grades like aluminium Si10 Mg, which which is having 10% of silicon, and it is increasing the absorption coefficient value of the material. But when you have to print pure aluminium, pure copper, it is very difficult to using a red type of laser. You need a very high costly lasers like blue lasers or the green lasers. Same in direct metal laser sintering. Instead of having a powder bed, you are having a laser, and you're having a coaxial nozzle from which the powder is coming. The powder is focused so that it should fall on the focus point of the laser, and it will melt the powder, and the powder will solidify or in a layer by layer fashion to make a 3D printing part. It is having problems like you can't print overhanging part. You need a 5 axis system to make a overhanging part. And the as for the same materials like copper, aluminium, silver, okay, and high even high melting point material like tungsten, like ceramics, this process is not feasible. So another process is wire arc manufacturing, which is quite famous now these days because it's also cost effective. You can use any type of big torch or TIG torch in a 3 axis machine or in a 5 axis robot, and can convert it to a convert welding process into a 3D printing process, in which you are having a arc generated, which is melting the material. It can be fed through the torch, or it can fed outside the torch. You can melt the material and join into layer by layer fashion to make a product. It is having a limitation. Similarly, having high melting point materials also, and also copper high thermal conductive materials, reflective materials, and the surface finish of these parts are not good. You have to do always some site of post processing to remove the cutting edges to get a flat surface or a high surface finish products. Another is electron beam welding. In this electron beam manufacturing, melting 3D printing machine, so it is having advantage of using electrons instead of photons. It is using electrons, and these electrons having good absorption coefficient to the high refracting material like copper. Copper can easily charge, and due to having good electric conductivity, and like silver, aluminium, they can be printable by this process. But this process is highly costly because it required a complete vacuum chamber, which is very costly to manufacture and also costly to maintain. The maintenance charges of this type of machine is very high because the filament is very costly and the chamber accessories are very costly, like deflection lens, focus lens, astigmatism lenses. These are very costly. So this machine is around 8 to 10 CR, but to make only small products up to 50 by 150 of diameter, you need a very high costly machine to make large products. So there are other type of processes which I'm calling as an innovative design cover innovative design aspects in EM, which is a indirect rapid manufacturing process. You can make a direct product using indirect method. It will be a metal 3D printing product, but we will start from polymer 3D printing. Like there's a very good example of investment casting in which people are using 3D printing wax or any other type of polymer as a pet trend, and it is used for investment casting process, and later on you are getting a final product. So this is also comes under indirect metal additive manufacturing, but casting is always having some issues. So there are some other alternatives, like you can have a polymer 3D printing part, and you can use a spraying machine and can try to spray metal on the polymer 3D printed part and to make it conductive. So this type of conductive parts can be used for like EDM electrodes, because it will have coating of copper material, which will be conductive in nature, and it will be give full channel to discharge and charge to make a plasma channel to for melting the workpiece for the cutting. And similarly, electroforming. In the electroforming, you can also deposit the electric material on the surface of the printed part to make it more conductive and to make it metallic. Another is investment casting, which I have already given one example. There is another method which is sintering, which is highly popular when you are dealing with the high melting materials like ceramics, like zirconia, you're having alumina, you're having silicon carbides, you're having nitrites. So these materials are highly melting point, and you can easily sinter it up to their 60 to 80% of the melting point, and you can get a dense part. Similarly, this process is highly useful for highly refractive materials like copper, silver. You can use aluminium. You can do easily sintering of this. If we can combine sintering with AM, okay, like a polymer AM, we can easily make a low cost, innovative, indirect metal additive manufacturing method. Let me show you. So we have developed this thing and filed a patent, and also it has been obtained, purchased by one company. So yeah, so start to understand this process. Important understanding is about the mechanism of the sintering. So sintering, everyone knows, is a fundamental process in manufacturing processes. Any type of manufacturing processes book, which is having when we are doing a powder compaction, where your powders, which is having spherical shape or irregular shape, can come together and can make, when you're heating it up at a high melting point, due to the thermal energy, the atoms at the corners of the metal spherical balls, it will be excited, and they will try to lose the energy to make bonds with another nearby atoms, and it will create a neck starting from the uh, nearby region of the metal particles, and it will grow, and later on it will look like this. So neck formation and pore size reducing is the second stage of the centering mechanism, and it will later end will make a spherical pore. So why it is spherical pore? Because let's see, if you are having three balls together, it will later on make a spherical pore, which is called as the final stage of centering. And because it is having equilibrium of energy at around 120 degree, and it will give you a complete equilibrium of energy, and it will not grow in this particular direction, and it will make a spherical shape. That's why it's not always 100% dense. This process gives around 99.9% density. When it will highly depend upon the powder size and powder shape. So when you are having a very large powder size, it will be cheaper. When you are having very small powder size, like nanoparticles, it will be more costly, but these are more effective. And the powder shape, and it should be more spherical. I hope everyone knows why we need a spherical particle for centering, because it is having high surface energy, surface area, to reduce the energy to the nearby spherical balls. So sintering can be done by different different processes, like a pressureless sintering, where you're not providing any pressure. It is, you're just placing a sample in the furnace. Another is electrical assisted sintering, where you are uh, putting pressure also and putting a electric charge on the sample, and it's giving you nearby 100% dense, and it's very fast, effective process. Another is pressure assisted sintering, where you are providing pressure also, and also you are providing the thermal energy for the sintering. Another is microwave sintering process, in which you are having a microwave energy, which is starting eating the sample from the inside and growing outside, and giving you very highly dense part, and it's quite fast. The heating rate of this process is fast. So out of these four uh, processes, so we can use only pressureless sintering and microwave assisted sintering for the 3D printing. Because if we are having a 3D printing part, we are having a 3D printing part which is complex in nature, and you provide a load, it will break the pores, because it will be having overhanging part. So you can't put any type of a load, you can't put any type of pressure on the 3D printing part. So you need a pressureless sintering. It's a conventional sintering in a tube furnace or in a muffle furnace, or it can be of a microwave sintering which does not have any type of pressure. So now we have developed the this process using pressureless sintering, and use it for 3D printing, and call it as a ultrasonic vibration assisted pressureless sintering. Now you will see I have started talking about a new word, ultrasonic vibration. Okay, so I will tell you why we had to use this ultrasonic vibration energy and for pressureless sintering. First, I will explain you the process, how this process works. Then I will tell you why we need a ultrasonic vibration. So in this process, like most all the processes of 3D printing, the first stage is making a CAD model. So you have to make a CAD model of a complex shape like this. We have making a form type of structure. This is a uniform form, and this is a graded form, which is having strut size varying in particular this direction. It is a thick curve, thick thickness, and this is having thin thickness. Okay, so we have taken two different complex shapes, and let's see, can we fabricate this type of part at the end of this process. Second stage is fabricating this part using any type of a polymer 3D printing machine. So it can be of stereolithography, SLA, any brand, Form Labs, any Cubic, any brand. It can be FDM, and FDM it can be any brand, and it can be of inkjet process. It can be polyjet process. It can be of any type of polymer 3D printing. It can be of LOM also, laminated object manufacturing process also, which is for polymers. Okay, so we have chosen SLA among these polymer 3D printing process because SLA gives you better surface roughness on the 3D printing part. So it is having very fine surface roughness as compared to other type of processes, and also this is very cost effective. The third step is to make a mold. Like in particular casting process, we are making a mold. Here we have taken a steel crucible, and we have put this sample 3D printing sample inside this crucible, and put a investment powder. So we have filled it with investment powder. So this investment powder was of it's a dental investment powder, which is a of phosphate based solution, and this is in a powder form, and it is mixed with the solvent. And this solvent, after mixing it with the solvent, when we are filling it in the crucible, due to the so it will solidify to make a solid investment. So it will be the investment powder will become solid, and it will complete a solid crucible. In the fourth step, we are putting this crucible in a furnace. It can be of any type of furnace, like a muffle furnace, where we have to heat this crucible up to 250 degrees Celsius, which is the evaporation point of this polymer, and it will burn out and will give you a cavity. It will give you cavity, and first important thing is here. So the polymer which we have chosen to make 3D printing, it was of a wax type of material because it is having a good uh, advantage. Like you can directly go from solid state to vapor state. You don't need to, so you can control it. You can have a many minimum time for the liquid stage, and so it will not give you cracks in the investment area. So you can directly make a crack free mold. So after having a free cavity, you can fill this cavity with the metal powder of spherical shape. So it can be of any metal. You can pick any metal. This process will work for TI6, for say FP, for any type of inconel. It can work for any type of material. So we have developed it for copper. So we have filled it with the metal powder of copper, and then we place it in a pressureless sintering machine, and we have done sintering. But here we have done another unique thing. Instead of having a normal pressureless sintering, okay, we have provided ultrasonic vibration. So I was mentioning we can't put any type of force. We can't put any type of pressure on this 3D printing part, but we can give another type of energy, which is a vibration energy, which will be at micron level, and it will enhance the sintering process. So I will tell you. So let's come to the, I will tell you in next coming stage what is the use of this ultrasonic vibration assisted sintering process. So the after doing sintering with assistance of ultrasonic vibration and high temperature, so you can get a 3D printing metal part which will be having the same shape as a CAD model. So this process is very cost effective. You can make the whole setup in a few lakhs, 2 lakhs, 3 lakhs, depend upon the cost of the quality of the accessories, and you can make parts after having like copper. If we are buying it for 10,000, you can make 20 by 20 lattice structure in only 2,000, which will be around 15 to 20,000 when you are making it with the laser based system. But it takes time. It's a little bit time consuming process. So in SLM you can make it in 3 to 4 hours, but here you need complete one day. But you can make multiple parts. You can make more than 10, 12 parts at a one time, and you can save it. And also it does not using the extra material like in powder bed fusion and SLM. You need a lot of raw material, but here you need a raw material which will be exact volume of the your product. So this is summary of the whole process, starting from the CAD model, making it using a polymer 3D printing SLI in our case, and making a 3D printing pattern, and making a mold by using investment casting powder, and then making a cavity by burning out the polymer, and filling this cavity with the powder, and doing centering with pressureless centering, ultrasonic vibration centering to make a final product. So these are few samples which we have made, and you can see it can use for any type of a complex shape. It's a octahedron shape. This is simple cubic shapes, and also the contamination. So as compared to the SLM, there is no contamination. This product is 99.99% pure copper. So let me talk about the setup now. So vibration, let me show you some results first, why we need vibration. So this left hand side SCM, you can see this is without any type of use of vibration, and right side is the use of vibrations. Okay, here you can see when we are using spherical particles, there are a lot of voids between them. But in using in the case of ultrasonic still pressureless sintering, you can easily get spherical pores, okay, at around 900 degrees Celsius. You can easily get it, and also it is done in 15 minutes. If you have to achieve this thing at 900 degrees Celsius with conventional sintering, you have to do it for 3 to 4 hours. Okay, so now you are getting spherical pores. If you remember this sintering mechanism, spherical pores signified this is the last stage of sintering. So your density is around 99. So you can't process this part further. It will give you some density, but it will be very slow process. You can't get 100% density here. So let me show you how this ultrasonic vibration assisted sintering works. What is the mechanism behind it? Okay. So in this setup, so important thing is your ultrasonic horn. So everyone has tried to learn about ultrasonic assisted machining and manufacturing processes, where we are having a ultrasonic generator, which is having converting the low frequency to high frequency signals, and then you are having a transducer, which is giving, which is generates a type of a piezoelectric transducer, which is converting electrical energy into mechanical energy, and later on this transducer is having very small size of amplitude of vibration, say around 4 microns. and which is not much enough for this type of sintering furnace required vibration. So you have to amplify it by using ultrasonic horn. Okay, so design of ultrasonic horn in this process is really important. So, and we have provided a cooling system also, which is on the ultrasonic horn. This is a cooling system, which is it's a jacket, and you're having 2 to 4 degrees Celsius of water which is flowing through this jacket, and it is preventing the heat to touch the transducer. So that your heat differential can't reach the transducer, and you can easily use a transducer and the ultrasonic vibration horn for longer time of centering. So the horn is look like this. This is actual printed, actual manufactured horn, which is having a transducer unit, and this is a your step size of ultrasonic horn. So this is very so design of this type of horn is very complicated. Generally, in excuse me, is there is a lot of disturbance.
Participant, please switch off your mic.
Thank you. So generally in ultrasonic machining, we are using a step size of ultrasonic horn, which is around like say 120.8 of the length. Okay, which is work on two anti-nodal points and one nodal points, where from the nodal points your vibration is getting amplified. Okay. So now this is very small horn. So, but for the around six nodal points, which is having and it is getting amplified at the step at the third nodal point, and you are getting same amplification at the right end of the horn. Okay. So you have to do a lot of FEM around this. You have to do model analysis, which is giving you the vibration frequency in the longitudinal direction. So it is really important because you have to take care of the diameter of the in the left hand side diameter d and small diameter d, and also about the length. It should have same frequency of 20 kilohertz, which is your transducer frequency for have the resonance, so that you can transfer the vibration from one end to another end. Also, it should have a longitudinal mode shape, so that the vibration should go in only one direction. It should not reflect to another direction. Okay, after doing this type of ultrasonic, this type of FEM adjustments, we come up with the length and the shape of the ultrasonic horn, and we fabricated and tested it with the ultrasonic vibrometer. So the vibrometer, laser vibrometer, to check the what is the actual natural frequency of this horn, and also the when you are giving resonance from the transducer, how much vibration is getting amplified. So it was around from 4 micron to 20 micron we were able to amplify, and which was enough for this powders for the vibration, because powder size was around less than 20 micron. So how this ultrasonic vibration works in the sintering process. Okay, first thing is when you are giving vibration to any type of powder, like you're having any type of powder, you give vibration, it will try to settle down. Okay, because you're having a rare fraction and a compression phenomena. It is trying to repel and trying to compress the powders, which is because the vibration is coming in a wave. Okay, so it will give time to settle the small particles under the voids of the large particles. So we have chosen mixture of the particle size. like having small particle size, large particle size, it was variable. When we are giving vibration at this stage, if we are having a small particles, small powder size, it can easily fill in the voids of the large particles, and it will give you uh, higher density of compaction. So powder is highly compacted using vibration at room temperature. So you're doing it at room temperature. So having higher density compaction at room temperature is giving you effective contact area to make necking, better necking as compared to conventional sintering. Okay, the first point of this one. And second point is rise in local temperature. When your powders are vibrating to each other, so it will strike to each other and it will generate energy, which is called as a flash sheet energy, and it will rise the local temperature, which is at the neck, at the effective contact area. So we have tested this with using a thermocouple at room temperature, and we have seen at the room temperature there was around 35 degree rise in the in the temperature of the powder as compared to the room temperature, which is more effective and at higher sintering temperatures. So if you are doing the sintering at 900 degrees Celsius, you will have around 50 plus 50 or around plus 100 degrees Celsius energy at the local area of the powders. So what is happening when you are having vibration at the effective area and you're having a local heat, so there will be chance of having dislocations, very small cracks at the very small, very nano cracks, dislocations at the effective area, contact area, and it give you if it reduce the material flow stress. Okay, it means when you are having you're having latex structure and you are having now dislocation, like this is your dislocation and this area is empty, so your material will easily, your another atom from the another powder will easily try to make bond with this one, because it will give you easy flow of material from one end to another end, and it will increase the rate of sintering to acquire high densified structures. So this is the example we have seen with the microscopic images, and we are getting spherical pores at lower temperature as compared to the conventional sintering process. So other than this ultrasonic vibration, there are a few other sintering parameters also, which is affecting this process. So we have tried to do some design of experiment using RSM methodology to make this copper cylindrical samples and try to do compression testing and try to measure the density. The results were very promising, and we have tried to make a mathematical model where we have seen sintering temperature is highly effective in for the getting highly dense part, and also ultrasonic vibration string percentage, because you can have 100% of vibration and can reduce it to like even you can go to 10%, but the most effective is from 60%. So we have chosen this range from 60 to 100 and have seen both are having a good impact with the high temperature and having local heating, which is delta T, which is coming from the ultrasonic vibration, is giving you better densification. So that was our observation uh, from these experiments, which we have which we have used it for mathematical modeling also. So we can see with the having ultrasonic vibration at easily at 950 degrees Celsius, we are getting highly dense part, which is around 99%, 9 tenths. So it's having isolated pores. It's a highly dense structure. So we have done multi-objective optimization and we have tried to fabricate heat sinks. These are heat sinks which we have try to fabricate of having different lattice structures, and also try to do some type of thermal heat transfer type of processes on this to know the what are the pressure drops, because when you are going through the high surface area lattice structure, how this copper based 3D printing process product can be used for better heat transfer. So we have also used this process to make complex structures like simple cubic forms and body-centered cubic forms. And I was discussing about graded structure, which is having a different variation in the lattice structures. And we have seen there is a beauty of having two different type of pores. One, you can have a design pores, okay, which is coming from your CAD model. Another porosity is micro pores, okay, which is at the strut of the 3D printing forms. So this micropores can be controlled. You can have less micropores, you can have higher micropores. It is giving you the advantage, like it can be if you are making it for biocompatible applications, okay, like for you're using titanium Ta64, so you can have better cell adhesions. If you're using for corrosion activities, so you can have fast local corrosions because you have a microporosity. So it can be used for a number of type of applications. So later on, after doing this work for the copper, we have seen, let's, can we use it for another type of different complex composites like copper and some carbon based composites. So we have tried to use it for copper and graphene composites, which at that time there was no paper on this copper graphene 3D printing product. So we were the first to fabricate and publish this paper. The important thing is people were trying to use this uh, copper spherical particle and mixing it with the graphene in a ball milling process. But you are damaging this spherical shape of the part. We need spherical shape, otherwise we'll not able to sinter it. So instead of using the ball milling, we have using the ultrasonicated for longer time, where we have tried to mix the graphene in ethanol, and later on we put copper and we mix it for longer hours in a magnetic stirrer, in an open magnetic stirrer, so that your ethanol can easily evaporate, and your copper can have addition of graphene. Like you can see, this is a graphene adhere on the copper substances, copper particles, and you're getting a spherical particles which is having same similar shape before starting the mixing process. Can we dried it in a microwave oven for 2 hours, and then we use this powder as a raw material for our doublet process. After going through this process, we were able to make composites of graphene up to 1.5 graphene percentage. Now there is a glitch here. If we are using conventional process, like you are not providing ultrasonic vibration, okay, so you will have a lumps of graphene. You're having lumps of graphene. But when we are providing ultrasonic vibration, your vibration amplitude were around 20 micron, okay, and you are having your graphene at the surface of the your copper particles. When you're mixing it, it is giving you homogeneous mixing, and your graphene is about distributed among all the particles and can easily give you better connectivity and better channel for the mechanical properties and for the electrical properties also. So we have tried it for tribological properties also, which is the ultrasonic assisted 3D printing part of copper graphene gives us better properties in tribological manners. Same, we have used this process to make this forms also and tested mechanical properties. And this we can see as compared to conventional process and as compared to ultrasonic vibration process. Ultrasonic vibration process is giving a better having better graphene distributed among the surface of the 3D printing part. So experiments are fine, but always it is good to verify the data with using some mathematical relations. So we have chosen the mathematical relation of a two spherical model by Rockland, which was given, which we are having a two particles having same shapes, having same diameters, and it you center, it will grow with respect to the rate x by a raised to n. A is your cross section, is a radius of the particle, and x is the cross section of the neck, which will grow with respect to temperature. Here T is your soaking time, means your sintering temperature, sintering time, or up to what time you have kept it for sintering. And B is depend upon your activation energy and Rayleigh constant. Activation energy is the energy required for the sintering. It depend upon material to material, and it is having T temperature. This is your sintering temperature. So we have chosen this model. Now, as I mentioned, in the experiment we have observed, instead of sintering temperature, we are having some local temperature, delta T, which was due to the ultrasonic vibration. Okay, so this vibration, we have added this delta T value here. Okay, and this delta T we have taken from a friction theory. This is a rise in temperature from a friction theory given by Bush in 2000, which is saying when you're having two contact of surfaces and they are vibrating among them with having some coefficient of friction and having some amplitude of vibration, it will have some delta T rise in the temperature. So we have measured this all this coefficient of friction value, ratio of amplitude, vibration, time of vibration for this process, and we come up with some delta T value. It depend upon the particle size to size. So we have kept a particles which are having same shape and same size, about 100 micron meter, so that we can effectively find out the values. So we have added this delta T in the main formula, and we try to measure it experimentally. We have done number of experiments like this one. We have done experiments at different temperatures and at different time, and we have calculated this x value and this a value. It's a 2a diameter. We have calculated this one, and we found out our results, and we try to fit the equation with the results, and we found out the n. If you see this equation, this is a very interesting equation. This is having n coefficient and into the power. So this n, if you can fit, if you're having both experimental values from the left hand side and the right hand side, and you just fit it this equation in this data, you will get n value, okay, which will be slope of uh, it will be slope of this equation by using least square method. Okay, so you can find out the n value. So as per the literature, if you are having some n value, so you can easily find out what type of sintering mechanism was there, because it is very important to know about sintering mechanism to get better diffusion, so that you can control the temperature, you can control the soaking time, and you can control the powder particle size. So you will able to know which is most efficient sintering mechanism for any particular material. So for copper, we have obtained, we're having surface diffusion and the volume diffusion mechanism were the more effective, so that we can have a similar result having ultrasonic vibration centering, and having with the experimentals also, and the prediction. So our predicted neck ratio value was the in the range of the experimental neck range value, and it is having a uniform distribution also. So this is we have developed this process, and we have taken care of the mathematical model also, and also taken care of the whole the experimental process, and so that we can use it for low cost process for fabricating highly conductive materials like copper, which are very difficult and nearby not possible by using laser based systems which are available in the market. So thanks for listening me. If you have any question, I would like to have those questions. Please feel free to ask any question.
Audience, if you're having question, please ask. Sir, regarding the finite element method of this your developed process, sir,
Yeah.
is it
ultrasonic on? Yeah.
ultrasonic on? So some
Yeah.
kind of FEM process, FEM simulation has been completed for this area?
Yeah. So we have done model analysis, and we have done the vibration amplification analysis.
Okay, sir.
Like
Wire additive manufacturing, we have to use some particular heat source modeling, no? Either if you are working in IC,
so yeah. So we are not use heat source model here. So for the ultrasonic on, we don't need to provide any heat source. We just need to the model analysis, mode shape. What is the mode shape? Okay, here we have for the your thermal energy analysis, we have used the mathematical model, not a FEM model. So it's a mathematical model, which is a relation between the parameters of this centering energy, which is the thermal energy, and the relation to energy, and the relation between the ratio of the radius of the particles and the neck growth width of the particles. You can make a FEM model also. It is not a, it's not a,
no,
not
because
much
it's a
difficult,
new,
but there is no use.
it's a new area for the researchers too. So and
Yes,
there is
yes.
a limited amount
Yes,
of work is
yeah.
available.
So yeah, there are many there are some models are available, but only for conventional centering, not for combining the ultrasonic vibration and the centering process. So there is a scope of research here, and this process can be used for even not with sintering process. You can even use it for welding. Okay, you can have a ultrasonic assisted welding where you can combine it welding and layer by layer manufacturing to make a new type of process. Like a VAM is there. You can use a ultrasonic vibration assisted welding and a layer by layer any robot or any 3-axis system. You can make a new type of 3D printing process. But it will need a lot of FEM modeling for evaluation of the temperature required for the bonding of the layers.
So apart from this copper and other metal, like which types of materials are there is scope for material like
I
so if you are
think
going to use for nuclear
we have
area
tried.
or some other.
Yeah, we have tried it for copper, titanium, iron, bronze, and tungsten. We had some tungsten material. We tried with tungsten also. So ideally, it can be used for all type of materials, but it depends upon the reaction between your investment powder and the powder. So if that investment powder, we have chosen the dental-based phosphate material, okay, which were not much effective. Okay, but if you have to make for platinum, for gold, so that will be more reactive material. So you can't use that material. So you need to find out an alternative material which can, like people are using platinum casting materials. Okay, casting, they are doing investment casting of platinum. So you can use those type of investment powder for in this process to for different type of metals. But it will be costly then.
Hello, Dr. Singh. Very good evening.
Very good evening.
I have a small doubt
Please.
that you are using ultrasonication method to give impact on the graphs, correct? So
No, not an impact. We are assisting.
Okay.
Please complete the question.
Yeah, the question is like, is there any effect of this ultrasonication process in these experiments? If it is there, then how
Yeah.
it is related to these results? Like the graphs what you're showing in that, I think the micrographs, SEM graphs you have shown.
Yeah.
In that variations are there. So is there
Yeah.
any specific ultrasonication utilization like this much frequency should be required and this much time required
So
to?
the thing is, so it depend upon whole your availability. Like we were having a transducer which were working on 20 kilohertz. Okay,
Yeah,
so
that is the
we
process.
have
that is the
yeah,
like you know
that is like you
ultrasonication.
can you no no that is you can have a transducer which is working at 40 kilohertz. Then you have
Okay.
to design your horn as per your frequency because you will not have resonance. And one
Okay.
important thing we have taken care if you the your the boundary conditions. Okay, here
Mhm.
your ultrasonic horn is on a one stand and which is fixed on a one stand as it like a cantilever beam. Okay, you don't have any other joint here. So this is your pipe and your this is your 3D printing part. So it is not
Yes.
joined to any other part of the machine. Okay, so we are trying to avoid any type of contact so that there should not be lack of any vibration lag. Okay, so we have kept it as a like a cantilever boundary condition, which is giving you effective uh, vibration in the longitudinal direction. But
Okay.
there is
Can
there is a
you?
lag. There is a lag. There is a lag. There is a limitation. Like this horn is of stainless steel SS 316. Okay, which you can't increase more than 1300 degrees Celsius because it's having vibration lag starting from 1100 degrees Celsius. We have done it at only 900 degrees Celsius. Okay, the furnace can work up to 1500 degrees Celsius, but we have only done work at 950 degrees Celsius maximum. Okay, because otherwise you need a titanium Ta64 horn which can go up to higher temperatures.
Okay, thank you.
Yeah.
Like variation of sonication is required for this process or not,
Yeah,
not required?
we have done it, but 100% vibration gives you always higher results. So this is a variation of ultrasonic power. We have
Yeah.
done it like from 20% to 60%. There was no much change in density, but from 60 to 100 there was higher density, and 100 was giving efficient results.
And in the error bar also, if you see the 60% power, there is a
Yeah,
huge,
yeah. There's a
like,
use that
yeah,
depend upon because you can't have a same type of a
yeah,
particle
correct,
size
correct,
in
correct,
every
correct.
part. Yeah,
Yes, 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 yes.
yeah. It will different. It will have always have difference.
Okay, okay.
Yes.
But anyway, it's a nice work. Thank
Thanks.
you.
Audience, anybody have any question, please ask. Session is open for question answer. Sir, for like as a FEM, so there is open chances for your under guidance from PhD scholars will be there for particular this area in the future.
So we have already like this is a the work is 1.5 year back we have done it, but recently we have done FEM modeling to find out the shrinkage and the deformation of overhanging parts happening during sintering, which are the parts which are made by 3D printing. It has been published in Acta so you can see there is a very lot of scope of using FEM modeling in this type of process because you need to know what will be the shrinkage and what will be the deformation in the shape after the sintering process. Because when you are having complex shape, you are having overhanging parts, so you can't avoid the deformation in the shape due to the gravity. So you need to model it first, because you can change, you can do alteration in the CAD process easily, so that you can have a perfect part which is required at the end. Yeah. Is there any other question from the audience?
Participant, do you have any question you can ask? Sir, this residual stress part point of view and some like because
So
it's a panel
residual
part.
stresses. So in sintering, there is not much residual stresses, because we are doing the cooling very slow. The cooling rate is very slow. So the solidification which is happening, it's a solid process. It's not, we are not going from liquid to solid state. So there is very less chance of residual stresses. Which, that's why this process, I would saying, it's having better properties as compared to the laser based system, because the microstructure is more controlled as compared to the laser based systems. This process is more efficient when you are making micro parts and very small precise parts. This is very efficient process.
Regarding your deformations, another point.
Deformation, that's why I'm mentioning there is deformation, so you have to do FE modeling. So we have done a lot of FE modeling. So I have not kept in the PPT. So their paper is already published. You can check my Google Scholar and can find, we have a recent published in Acta Materialia. So you can check those papers. There are a lot of, because their deformation is highly important in this sintering process.
From audience, anyone is having question, please ask.
So if there is no question at the moment, please feel free to email me. So you can find my email ID at IIT Bombay Mechanical Department website. If there is no any
There is
question, so
one
we, yeah,
request from
please.
one person that they are asking your presentation. So is it
Presentation,
okay
sure.
to
I will.
share?
I will share. I will share presentation. All the things are already published, so I will share the slides.
Sir, contact details, everything is available on
Yeah, yeah.
IIT Bombay website page. You can
Yeah,
go
yeah.
and
IT
see it.
Bombay. Yeah, yeah. Also on my PPT, it will be available. I will share my PPT.
So finally, thank you to Dr. Raghuvinder Singh. Myself, Dr. Preetham. I got the opportunity to give the vote of thanks on this program. So many thanks to Dr. Singh from the Aditya University that he has accepted our invitation and he given his time to us. And I hope all the participants got some knowledge from his this session. And he is an expertise in different area. What he has explained, additive manufacturing, biomanufacturing, and many more things are there. Powder metallurgy, especially. And we all are delighted and knowledge from your lecture. So thank you, Dr. Singh. In future,
Thanks,
if
Dr.
we
Preetham.
require, definitely again we'll
Yeah,
give
sure,
a
sure. It will be good to
yeah
have offline sessions.
yeah
In
we are
offline
trying.
session to have better interaction. Yeah.
Yes, we are trying for that also.
Yeah, so I
Next,
also encourage your BTech students, because we are always having a lot of internship offers at IIT Bombay. Please feel to have a bright student from your college to apply as an intern at IIT Bombay, so that they can have better flavor of research activities.
Yeah,
doing
yeah,
work with the
that's why
PhD.
we are also trying. We are trying to have a MOU with different organizations, QS organizations, and our NRF organizations. We are trying because recently we have approved as a university, and as part of research also, many of that like in our university, a lot of doctors are there and they're doing in different areas of research. Definitely we will contact you regarding this students intensive and this collaboration of project and research.
Sure, sure.
But thanks once again to you that you offered from your side.
No,
before us.
Thanks for
Yeah.
calling me.
Yeah,
Thanks
yeah,
everyone.
thank you.
Yeah, please feel free to email if you have any query.
Yeah, definitely we'll share all your information to our audiences, our staff, like those are the attendees are there, and we'll also in contact with you.
Sure. Yeah.
Once
thank
again, thanks to you and all the audience. So our next session will be started exactly 7:30, and if you're having work, you can meanwhile you can leave and again you can join exactly 7:25. Thank you once all.
Feedback link I will share within soon in WhatsApp group. You can just give the feedback. And I request participant, please, if you're having any doubt, you can ask a question directly to the speaker. Because the speaker can be, he can give answer in a proper and broad way because he is expert of a particular area.